Let's go back and let's start with what I have to say today. So today we are closing the chapter on models and isometries. So first, some final considerations on the groups of Riemannian isometries, and some words about one more model, which is not, we're not focused on it a lot, but it has some useful properties. So first, some kind of a it's like an infinitesimal lemma somehow. You see, what it says is, okay, suppose you have a Riemannian isometry of the Poincaré disk that fixes 0. You see, so you know that it fixes 0. So you know how it behaves on one point, right? So you know it fixes 0, and also in that point of which you know that behavior, you also know the behavior of the derivative. Okay, so just from knowing, you know, this infinitesimal behavior at one point, so 0 goes to 0, and at the level of derivative, it behaves as the identity. Just from knowing this, you can deduce, you know the behavior on the whole disk, right? So I would say this is kind of a bit surprising, I would say. And somehow I would say also that at least morally is reminiscent of the fact that that we are talking about that somehow the Riemannian isometries are really all of them given in terms of holomorphic functions and maybe these reflections. Right? And so somehow I would say this is really reminiscent of the fact that all of them can be described pretty much in terms of holomorphic functions. Okay, so for the proof, I mean, so first of all, notice if I have one such nu fixing 0 and with its derivative being the identity, what I see is, look, the determinant of this one is 1. It's positive. Right? So nu has to actually be an orientation preserving Riemannian isometry. Right? Actually, any Riemannian isometry as the level of derivative, either it has either positive determinant everywhere or negative determinant everywhere, but it cannot have positive determinant in some points and negative determinant in the other points. Right? And somehow somehow that's the reason. Right? Okay, now since we have an explicit formula for the elements here, that is, we know that all of them are given as Mobius transformations associated to elements of SU11. Well, we can write nu that way. And now, since nu of 0 is 0, well, we can immediately deduce that beta is 0. Okay, and now the derivative is, well, nu is a Mobius transformation, and we computed the derivative of a Mobius transformation, so it's multiplication by this complex number, which is just 1 divided by the square of alpha conjugate. So, since this is the identity, what I obtain is that this number has to be equal to 1. So alpha conjugate has to be plus or minus 1. Right? So this means that here in this matrix I have beta equal to 0 and this equal to plus or minus 1. So this one is also equal to plus or minus 1. So I have, so this is how it looks. Okay, but in either case, you see, in either case, like even if what I have here is -1, the Mobius transformation is the identity. So, which is what I wanted. Okay. So I would say this is a kind of a very strong lemma, right? So just from knowing the behavior at one point and the infinitesimal behavior at one point, you know everything somehow. Okay, and now state and prove the corresponding lemma, but in the hyperboloid. Right? Let's say where the special point here is now it would be 0, 0, 1, right? The north pole. Okay, now the point of doing this is that now we can finally prove something that we left incomplete, right? Which was showing that the groups that we encountered are actually already the whole groups of orientation preserving Riemannian isometries and the whole Riemannian isometry group. Right? So if you recall, we showed that this, which was the orthochronous Lorentz group, was contained here, and we showed that this, which we called the restricted Lorentz group, was contained here. But at that point, we didn't manage to show that there was equality. So now we are going to prove. There are two possible strategies. One strategy is instead of doing what I'm going to do, is go to the upper half plane, use the fact that in the upper half plane you already know everything, and come back, or what I'm about to do. Yeah. So this we already know. These inclusions. That's what I just said. And so now take. I'm going to show this equality. So I'm going to take phi here. Yeah. So I take phi there. And now for this phi, you see for that phi, I look at what it does at 0, 0, 1. So, sorry, this dot should be here, not here. Okay, but so I just look at phi of 0, 0, 1. Right? It's at some point in the hyperboloid, and I look at its derivative at that point. So that of course that I can of course do. Right? Like just look at the behavior of phi at 0, 0, 1 and its infinitesimal behavior also at 0, 0, 1. And the point is that there always is, so at least that infinitesimal behavior can be realized by a matrix. Okay, and somehow the objective, you see, we want this equality, so really the objective is show that phi is given by multiplication by some matrix. Yeah. Yeah, so right, I mean, we still don't, I mean, we take this one here, and we still don't know whether phi is multiplication by some matrix. We still don't know. I completely agree, right? But if you let me maybe draw the hyperboloid. So you have this point, right? And you can definitely locate its image under phi, right? I don't know, let's say here. Phi of that, so phi 0, 0, 1. That you can definitely do, yeah. Right? And somehow for this point, you can definitely consider all the matrices in SO to 1M, I mean in the restricted Lorentz group that take this point to this point. There definitely are, and there are many. Right? And among those, there is exactly one. Well, I don't know if exactly one, but there exists one that has also the same derivative. And so somehow what I'm claiming is only that there is one matrix here that has this behavior on the point and the same infinitesimal behavior at that point as phi. But somehow I still have a long way to go because because if I take another point, then I agree. Then I don't know that it's the same matrix. Right? Yeah. So yeah. Okay. But you see, somehow the point is that I am really kind of in some situation similar to this lemma, where I know only the behavior at one point, including infinitesimal behavior, but only at one point. That's the situation. And so what do I do to really since this lemma is given in terms of a point being fixed? Well, something I can do is go from this point to this point using A and come back using phi inverse, so that now this point becomes fixed by here should be phi inverse, right? And so now I'm in that situation, and somehow, since also the derivative of the derivative according to A is the same as the derivative according to phi, the derivative going via A and coming back via phi is also the identity by the chain rule. So using the corresponding statement, but for the hyperboloid, I can deduce that the whole composition is the identity, and that's the jump, right? Where now from here I can say, okay, the matrix that did the job for this point does the job everywhere. Yeah, and so somehow my point of showing this lemma first in the disk is that since the disk and the hyperboloid are isometric, Riemannian isometric, you can just maybe for the hyperboloid just go to the Poincaré disk and come back to the just to deduce the corresponding statement from the fact that we already know this lemma. Okay, so that shows that you see that phi is equal to A, and then phi is really here. And then exercise show the other inclusion. Right? So show this inclusion. I mean, you can just try and repeat the idea, right? Or adapt the argument. Okay. Now, by the way, this is a handing exercise. So let me just go first. So somehow, so it's like, without assuming that we have proved any of the results, right, of today, show that for any orientation preserving Riemannian isometry, there is one matrix realizing the behavior of phi at this point and its infinitesimal behavior as well. Okay, so proved kind of that key point. I would say it's a very instructive exercise. I mean, I think it's a fun exercise. I mean, you have, yeah, at some point you really have to play with the fact that the stabilizer of the North Pole is isomorphic to the circle. Okay, now Beltrami-Klein's model. So it's a fourth model of the hyperbolic plane that I have actually already mentioned. So here in this picture, where as you may remember, from the South Pole I can stereographically project from the Poincaré disk to the hyperboloid. Right. Yeah, okay, so I can do that, right? But yeah, but for sorry, I was about to mix two different ideas. Sorry, let me backtrack a little bit. Instead of projecting from the South Pole, now what I'm going to do, you see, instead of projecting from the South Pole and placing a disk at height 0, right, at the origin, what I'm going to do is move one unit upwards, and then just project from the origin, and then now take a disk at height 1. And this disk at height 1, it's the Beltrami-Klein disk. And now you see in the hyperboloid shortest curves we saw they are of the form intersection of the hyperboloid with some two-dimensional plane passing through the origin. If you take the intersection of such a plane with this disk, you see, like at height 1, you obtain a segment of a straight line, right? Because you were talking about a plane, right? Okay, so you see the shortest curves of the hyperboloid are mapped to Euclidean straight line segments in this disk, in the Beltrami-Klein disk. Okay, so the model of Beltrami-Klein is simply this unit disk, the unit disk, and now you declare simply that the shortest curves are the Euclidean straight line segments, and by the stereographic projection from the origin, if you place the disk at height 1, they really correspond to the shortest curves in the hyperboloid. Okay, so there is geometrically is kind of not very well behaved, in the sense that when you take two shortest curves there, so if you take two of them, like let's say this one and I don't know this one, their hyperbolic angle of intersection is not the angle that you see. It's not the Euclidean angle. So in other words, this is a so-called non-conformal model. So it's useless for measuring angles, or almost useless if you want. I don't want to say just useless, but it's not very useful if what you want is measure angles or speak about conformal maps. But how is it useful? Well, since the shortest curves here are just segments of Euclidean straight lines, the hyperbolic convex sets in this Beltrami-Klein model are simply Euclideanly convex. So somehow in the advantage of the Beltrami-Klein disk is that hyperbolic convexity in the Beltrami-Klein disk coincides with Euclidean convexity. So whatever you know about Euclidean convexity, you automatically know about hyperbolic convexity in the Beltrami-Klein model. In particular, for instance, there is maybe I'm going to leave it as an exercise. So you see, this is I think this is in general. If C let's say in Rn is an open convex set, and I mean just Euclideanly convex, right? I mean in Rn, then it coincides with the interior of its closure. Okay, so this I leave as an exercise, and for instance, since now since in the Beltrami-Klein model, shortest curves are just segments of Euclidean straight lines, I automatically know that if C now is an open convex subset of the Beltrami-Klein disk, I don't know, let's say BD for BK for Beltrami-Klein, then I automatically know this. But then I also know that for the other models, because you see their stereographic projection from here to the hyperboloid will sends shortest curves to shortest curves, and it's a homeomorphism. It's actually a diffeomorphism. And from the hyperboloid, I can pass to the Poincare disk and to the upper half plane. So you see, just from this exercise, using and with the aid of the Beltrami-Klein disk, I can also say that if I have a hyperbolically convex open set in the hyperbolic plane, then it coincides with the interior of its topological closure. Okay, so this is the type of advantages that the Beltrami-Klein disk gives. By the way, showing this without using the Beltrami-Klein model, it can be very hard. Okay, so a couple of pictures that we had already seen.